Hi, it's a great pleasure to introduce Niv Buchbinder, who's visiting from Tel Aviv University. He's here on sabbatical at UW and Microsoft for the year, so you should definitely talk to him. And today he'll tell us about submodular maximization.
Thank you. So what I'm going to talk in this talk, so I'm going to give you some introduction of what submodular functions are and why they are interesting. So I will not assume that you already know what submodular functions are. And then I want to give you the most clean concepts and elegant algorithmic ideas that are used for submodular maximization. So in this part, I will show you many algorithms and many proofs. I'm cheating in many places, and I don't even remember where I'm cheating. So in some cases, I will tell you that I'm cheating. In other places where you catch me cheating, I will claim that this was on purpose and that it is easily fixable. But the idea here is to give you really the elegant and the ideas, and this is why cheating is kind of good. And I want, if you want to ask many questions, I will get to the more advanced places and open questions, and I will give you actually many tips on how to order more efficiently in restaurants. So this is the most important thing in this talk. So let's introduce what are submodular functions. So here are two meals. This is a small meal. This is a larger meal with more dishes, right? And we ask ourselves, what is the added value of this dessert to this meal and this meal? And then you see that this meal is larger and it already has a dessert. So what you should all say is that the added value is higher where? In meal one, the added value is more. So this is the right answer here. If not, we are in problem. And this motivates the main idea of submodular functions. So here is the formal definition of submodular functions. So we have n items. These are the n dishes. We have, right here, we have a non-negative submodular function. So it gives any value to subsets of items. And then this is the added value of the dessert to meal A, and this is the added value of the meal to B. And if B contains A, so if A is a subset of the dishes in B, then the added value is more for A than for B. So you should remember that added value is more for smaller subsets. And in some places in this talk, but not too many, I use this notation. This is just the marginal value. This is just a short of this FA union U minus F of A. So this is the definition that I will use, but actually this is the real definitions and they are equivalent, but you should think about this definition throughout this talk. So here is another example. So just to be sure, so we have subset. We have 3 items, right? We have all the subset of 3 items, and these are the values. And I'm telling you this is submodular. It's not easy to check this. But for example, adding a banana to a larger set has decreasing value, decreasing marginal value to add the banana. So as you can see with this example, so keeping a representation of all the function can be very large in some cases. So you should keep values for all subsets of items. So what we assume here, and this is assumed in many other places, is that you are given a simple oracle that if you give it a subset of items, it will just return you the value of the item. So you have access to the function only via this value oracle that gives you value to any subset. So if I give you a meal, you should tell me what is the value of this meal for you. This is the value oracle. There are other oracles, but we will speak here only on this value oracle. So here is the last definition for now. So monotone functions. So we will speak about monotone submodular function. A monotone function is a function in which additional dessert never hurts. So if you add more and more dishes, value only increases. So you know this is not always the case. But in some cases, you can assume this monotonicity. So monotone value, if you add more, you don't lose money. But in principle, you can lose money. And here are 2 more concrete examples of submodular functions. So one of them that you can think about is coverage function. So what is a coverage function? You have elements which you have a set cover, which is elements, and you have sets, which are subsets of these elements. And then the function, given a family of subsets, gives you how many elements you cover, or what is the area that you cover. And if you look at it, right, if you add a set to a larger family of sets, you cover less and less. So you can convince yourself that this is a submodular function and a monotone submodular function. So this is a good candidate to think when you think about monotone submodular functions. Here is a non-monotone submodular function, which is very important. So this is the cut capacity function. So you have a graph, directed or undirected, with capacities or maybe unweighted graph. And then you give me a subset of the vertices, and the function measures the size of the cut or the capacity of the cut of these subset of vertices. So it's not trivial, but you can check that this is indeed a submodular function, but it's non-monotone, because if you add another vertex, in particular if you add all vertices, then the cut decreases. So in some cases, adding more items decreases your function. This happens in the cut function. So there is a lot of motivation for submodular function. Most of it I don't know even, but in combinatorics, algorithmic game theory, right, the value of items, learning and game theory, all over the place there are submodular functions. So what can we do with the submodular function, or with function in general? We can either maximize it or minimize it. And since maximization is much more fun, then here we will only maximize a submodular function. So it's also very interesting to minimize submodular function. But here we will deal only with maximization. So what is maximization? So here is a problem. Just find the best meal. So I give you a set of dishes. Find the best meal that you can have. So this is interesting only in the non-monotone case, because otherwise you just add everything, right? But in the non-monotone case, this is interesting. And this generalizes, for example, the combinatorial problem of max cut or even max directed cut. We can also choose other constraints. So here are other constraints. Find the best meal of 10 dishes, for example. So I give you, you can choose at most 10 dishes, and then find the best meal. So this is a constraint problem. It generalizes max k coverage, if you know the coverage function, or max cut with specified size on the cut size. So this is an important problem. And in general, you can have many other constraints, so exactly k elements, and packing constraints, metroid, all are interesting. And here, the most general, we will deal with this metroid constraint. So I will just tell you what metroid, although it's not so important to get everything. So metroid constraints are what? You have n elements, and then you have a collection of subsets, a feasible subsets. They are called independent set. And the two properties that they have is that it is down-closed. So if A is independent, and B is a subset of A, then B is also independent. And this is the nice property of metroid. So if you have two independent sets and one is larger than the other, you can add one item from the larger set to the smaller set and remain independent. So this is the main property of metroids. Here you don't really need all the power of metroid. You can think, if you want, on graphic metroid. So graphic metroid, you have a graph. Elements are edges, and they are independent if they contain no cycles. So a spanning tree is independent, for example. But here, for most of the talk, except for the very end, you should really think about very simple metroids. One is just find the best k meal. This is find the meal with at most k dishes. And this corresponds to a uniform metroid. And the other option is find the best balanced meal. So I give you, you can choose at most one main course, for example, one side, one glass of wine, and one dessert. So this corresponds to what is known as a partition metroid. So keep in mind these two problems. These we will follow and give nice algorithms for these problems. Okay. So to warm up and to get some notation, let's start with the first idea that people tried already in the 70s. And this is the greedy algorithm. So how would you maximize? Just choose a greedy. So suppose we can choose at most k elements. So what can we do? We start with an empty solution. Then we look at the element that contribute the most currently to our solution. We add it to the solution, and then go back and choose another and another dish. So this is the simplest idea maybe that you can think about for maximizing a submodular function. And actually, it's quite good. So already in the 70s, people proved that this is 1 minus 1 over e approximation if you have a monotone submodular function. We will prove it in the next slide. This is just one slide. And actually, this is the best possible. So this is the best possible for maximizing monotone submodular functions.
This is
under cardinality constraints.
Cardinality constraints and with the Oracle model.
And with the Oracle model, yes. We are always in the Oracle model, and this is for cardinality constraints. I will say in a minute that it's not tight for others. So let's prove it, because we will use these ideas later. And the proof is really nice and elegant. So this is Si is the solution at time I, and Si minus 1 is the solution at time I minus 1. So remember, we are adding the best element to Si minus 1. So this is certainly better than just adding the average adding of any subset, and in particular the subset of opt that we can add. So this is using the greedy step. Now, this is a property of submodular function that I didn't prove, but it's quite easy to prove. The property is that adding any element independently worth more to the function than adding all of them together. So adding all the elements of opt is less than adding each element of opt separately. This is by submodularity. And then by monotonicity, we see that Si minus 1 cannot hurt opt. So this is at least f of opt, right? Minus f of Si minus 1 over k. And this is all the proof. So from now on, only we need to just rewrite this inequality. And if we rewrite it, we see that the gap, this is the gap between opt and our current solution Si. It is decreasing by a factor of 1 minus 1 over k with the gap with respect to the previous iteration. So after k iterations, the gap is 1 minus 1 over k to the k, which is roughly 1 over e. And then since the empty set, this is the empty set, is non-negative, so it is or 0, you can assume, then this is f of sk is just 1 minus 1 over e of f of opt. Okay, so this is the whole proof, and it's quite nice. So let's see what is good and what is bad about this greedy. So let's start with the good news. So the good news we already said and proved, it is 1 minus 1 over e approximation for monotone submodular function subject to cardinality constraints. It's the best possible in the Oracle model. It's deterministic and it's simple, right? There is nothing simpler than this greedy. So the less good news, but still good, is that for partition method, if I give you just to choose one main course and one dessert and one glass of wine, this is only a half approximation. It is not the best possible. We will see later a better algorithm, but it is still good. The really bad news is that it has no guarantee if the function is non-monotone. So if dessert can hurt you, this has no guarantee. So let's see why, and we will try to fix it. So here are the dishes in the restaurant. And as you know, chocolate cake is the best dish, right, in the restaurant. This one has value 2 over the empty subset, and all the others have value 1, right? So the greedy algorithm just consider these values and will choose right away the chocolate cake, right? But here is all the function. So the function, really all other dishes combine well. So if you choose 2 of them or 3 of them, you will get the size of the number of dishes that you choose. But if you choose chocolate cake, or if you add it to any subset, it will reduce automatically the value of it to the value of chocolate cake, which is 2. Right? So chocolate cake can really hurt you, right? If you add it. And then what you see is that if you should choose 10 elements, right, you are able to choose 10 elements other than the chocolate cake and get 10. Chocolate cake will give you only 2. So this will not have any guarantee. Okay? So we will try to fix this problem later. But first, what are the interesting questions that I want to speak about now? So now we're ready. So one question that is interesting is what is the best approximation that you can have? So both from monotone and non-monotone functions. And we will speak about metroid constraints, but again, you can think about partition metroid, for example. So this is the first question. And the second question is, can we get this approximation by a deterministic algorithm? So currently, we only saw deterministic algorithm. We will see many randomized algorithms. So this has motivation, right, because we don't want randomization. And in particular, it's not clear if we need randomization or not. We have an oracle. We don't have an access to the function. So it's not clear if randomization here is required or not. But in general, if you don't like to get your meal in expectation, then you probably want to run something deterministic. So what are the answers that are currently known and what I will tell you? So these are the upper bounds. These are the best things that you can get. These are information theoretic with the value oracle. So you cannot get better than this if you only access polynomial time the oracle. So for monotone, you cannot get better than 1 minus 1 over e, which is 63%. For non-monotone, the best bound currently is 47.8%. What is known? So randomized algorithm. So for monotone functions, and I will show you an algorithm that gives you this, just a sketch of this algorithm. I will show you how to get 1 minus 1 over e for this. This is much better than half of the greedy.
This for any matroid?
For any matroid, yes. I will show part of it. I don't have a lot of time. And I will try to show you how to get for non-monotone functions 38.5%, which is the best known. Probably both of these are not tights, and this will be the open question at the end. Now, for deterministic algorithms, we understand even less. So for non-monotone, the best algorithm for metroid is 1/4. And I will try to show you how to improve the monotone. So you will be able to get a meal which is not 50% of the optimum, but 50.08 of the optimum. We will see how to improve the greedy algorithm. So I want to show you this kind of this, part of this, and part of this. This is the goal, depending on how many questions you will ask. But I want to mainly show you ideas and techniques, so the clean techniques. So first, let's fix the greedy, right? So we try to answer now the question about maximizing non-monotone functions, and greedy does not give you any guarantee for non-monotone functions. So let's see how to fix it. So here is an idea how to fix it. You start with an empty solution, and then at each round, instead of choosing the best item that you see, you look at the k best items, so the k items that contribute the most to the solution right now, and then you choose one of them at random, uniformly at random. So first, let's see why it's good for the chocolate cake example. So what will it do? So remember, chocolate cake worth 2, all other dishes worth 1, right? But chocolate cakes ruins everything if you just add it. So in the first few rounds, 2 rounds actually, chocolate cake will be one of the best items, but you will pick it up with very small probability. Think about k as large, right? So you will pick it with small probability. And then later on, after you added 2 items, you see the chocolate cake is really a disaster to the meal, right? And then it will not even appear in these k best elements. So you kind of avoid with some probability the chocolate cake, right? And actually, you can prove that this random greedy is not worse than just greedy on uniform metroid for cardinality constraints in the monotone case, but it gives you some guarantee of 1 over e to the non-monotone submodular functions. So the main idea here is try to avoid, to add randomization, to avoid like a bait. Don't go directly with the chocolate cake. Look at the other things in the menu. Yes?
Can't you have k copies of the chocolate cake?
But what is the marginal with respect to all of them? If you have k chocolate cakes and everyone worth 2, then take k chocolate cakes.
No, it's still a good point, though. If there are k copies of the chocolate cake and k copies of, or 2k copies, or anyway. The point is the chocolate cake will show up amongst those best
but
items.
Then they should combine, so it's submodularity. You will not be able to build such an example. So actually, let's prove it. I will not prove it fully, but I have more slides at the end that I probably won't be able. But let's see why it's for monotone function, and then I will tell you why it's working for non-monotone functions. So this is the same proof, actually. So the only difference here is that I added expectation here. So fix everything that you chose up till now. So you fix everything. So this is fully deterministic. Then, right, you choose among the k best elements. This is best when choosing uniformly out of the k elements of opt. And then everything else just go together, right? And then this is true for every SI. So you can unfix the event. And then you see that the gap between opt and the expectation of SI is decreasing by a factor of 1 minus 1 over k by the gap between SI minus 1. And the proof is just the same. Okay? So just randomly choosing amount of k is as good as just picking the best one. For non-monotone function, so what goes wrong? So here is where I used monotonicity. So right, chocolate cake can hurt opt. So this inequality is not correct. But what is good about this random? So what you can prove, this is another slide, but I will not do it, is that if you choose each element, if you choose an arbitrary set and you choose each element with small probability p, then the expectation of how much it can hurt opt is no more than 1 minus p of f of opt. So if you choose each element with 1%, then opt still have 99% of the value. And then what you can see is that what is the probability that you choose the chocolate cake? So maybe it appears in the k best all in round 1 and 2 and 3 and 4. But then we will not pick it in each round with probability 1 minus 1 over k. So the probability that you do pick it is less than 1 minus this value. And opt does not decrease by a lot. So this is not opt, but some fraction of opt. And then if you plug this into the inequality and solve the recursion, you will get the 1 over e approximation. Combinatorial approach that I show you, like choosing randomization and so on, fail to give these better bounds for more general metroids. I'm not saying that they are not able to give these bounds, because later on I will try to convince you that these algorithms should give you the same bounds. But in general, right now, they fail to give these bounds. And what people try to do is try to go to relaxations. So this is the next idea in maximization of submodular functions. So what is a relaxation? So in the linear case, probably most of you know what is a relaxation. So you want to find the maximal value in out of feasible integer solutions. So you first take the feasible region and take maybe the convex hull of this region. So you make it fractional. And then you also use the fractional value. If you took one element with probability half, you give half of the value in the objective function. So you want to do the same for submodular functions. So here is, you take the feasible region, you make it a polytope. But then you ask yourself, how can I extend the function fx to a function over fractional solutions? And there is flexibility here. And it turns out that for maximization problem, a really useful extension is the multilinear extension. So what is the multilinear extension? This is a really simple concept that you can think about. If you have a fractional vector in 0, 1 to the n, you just take the expected value of a random subset that contains each element with probability exactly xe independently at random, right? So actually, if you write it explicitly, which is a long term, it's just f of s, and the probability of f of s is the product of xe in s, and 1 minus xe is not in s. Okay, and you can observe easily that this is indeed an extension. So if the x is integral, this gives you exactly the function. So this is extension that was really useful in maximizing, and it has many nice properties that I will not prove here, but I will tell you some of them. So you want it to be maybe convex or concave, but it's not. But still it has nice properties, so it retains the properties of some modular functions. So for example, if the function is monotone, adding an element will not hurt you, then the derivative of f is non-negative. The second derivative by xe is always 0 because it is multilinear, right? But the second derivative by xi and xj is always non-positive, and this comes from submodularity, from the fact that adding ei to a larger subset worth less than adding ej to a smaller subset. But here, for our discussion, we actually need very few properties that are kind of the same, at least in notation, as in the case of submodular and discrete algorithms. So this property, so this v is, I will say union or intersection here. It's just the maximum coordinate-wise. It is saying that adding elements of a subset A to F gives you more value than adding all the elements together to the subset S. So this has the property in the case of the multilinear extension. If F is monotone, then adding more elements will not hurt you. This we will use. And then if you take and manipulate the function, you see that the derivative with respect to xe is just the marginal value of adding the element divided by how much you are left to add. So 1 minus xe. And here is one place where I cheat, and I will say later that this is really cheating, is I assume that you can actually take the value of f of x and the derivative of f of x, and this is not the case in general. You just have an oracle to these values. But let's assume for now that we have exact values for this function. So what should we do if we want to maximize a submodular function? So as we use in other relaxation, we solve the relaxation, maybe approximately, and then we round the fractional solution, and then maybe we lose more. So actually here, rounding is a real issue, and there are lots of ideas there. In some cases, it is not an issue. For example, in the unconstrained case, you can just simply toss a coin and choose each element independently, and you get exactly the value of the multilinear extension. But in other cases, sometimes you lose and sometimes we don't. But we will not deal with this issue. And in case of the metroid constraints, you don't need to lose anything in the rounding phase. So you lose only in the solving the relaxation. So this is the main issue in this problem. So how do we solve the multilinear relaxation? So this is the real issue. So we have maybe the metroid polytope, but you can actually assume that it is just a down-closed polytope. So a down-closed polytope is just a polytope where if y is in the polytope and x is less than 1 coordinate-wise, then x is also in the polytope. And this captures all the constraints that we've seen so far. So metroid constraints, partition metroid, cardinality constraints, everything. And then you ask, how good can you solve the multilinear extension on these down-closed polytopes? So this is where the hardness comes from. The hardness is less than half. And the algorithm are slightly improving. And this is already old. So this should already be improved. And I will try to show you how to get this 38.5%, or the ideas of how to get them. In the monotone case, this is actually close the problem. So there is an algorithm that gives you 1 minus 1 over e for the multilinear extension. So I think I will skip the proof, but I will just tell you what is the algorithm, and I will show you that this is only 3 slides that I will skip. So what is the algorithm? It's just a measured continuous greedy. So what you start from an empty solution, from a solution with all 0, and then I will describe it continuously. So over time t, this should be discretized later. So what is the greedy step? You take xt, which maximizes the marginal contribution. So you look at the marginal contribution to your current yt up till now, and you find the best x in the polytope that maximizes this. So this is actually a linear optimization over the polytope. So you assume that the polytope is what is called solvable. And then you don't decrease to the xe, but you punish coordinates that are large. So you punish a coordinate by a factor of 1 minus the value that it already has. So this is the idea. And what you can prove is that, so this is the whole analysis, and I will skip it.
Sorry, the top line.
The top line is the algorithm.
No, I know, but just what's written on the right in the parentheses, that's the e's coordinate of x, or?
Yes. Yes, actually, this is the e coordinate. This is the sum over e of this times xe, and you are trying to maximize it. So you're trying to maximize a linear function over xe. X is in the polytope. With respect to the current solution. So analysis is not too difficult. You need to prove feasibility. And this actually uses the same inequalities that we used to analyze the greedy algorithm. So it's again use the fact that adding one element at a time gives you more value than adding them together. So this is the whole idea. And then again, this is the main idea. So in the monotone case, you just get here that here you gain more value than what the direction to opt will give you. And then you solve this differential equation and get 1 minus 1 over e. In the non-monotone case, you use again the fact that if you don't choose an element with large probability, it will not hurt you too much. And this is why you punish elements if they were chosen before. And then you get a different recursion, and you get actually the 1 over e that we got in the random greedy. And basically, it's the same analysis, more complex. It's slightly more complex. So I don't have much time, so I'll just tell you how to improve this to 38.5%. So this requires another idea that was in the literature already. So there is continuous local search. This is just a continuous gradient ascent. And what you can prove it for submodular function, it will give you a vector which is at least half of the union with opt and the intersection with opt. So think about z here as an integral solution for now. So this algorithm does not give you guarantee by itself, but the idea is the following. So either z is a good solution. If it is a good solution, then this is great. Otherwise, what does it mean? So it means that this value is small. So z intersection with opt is small. So z, the local optimum does not contain a lot of opt. And z union opt is small, meaning that actually adding z to opt decreases your value, so it hurts you. So the conclusion here is that you should really avoid the element of z, at least at the beginning. Right? So elements of z, if this value is small, elements of z are not good. They are not of the optimal solution, and they don't contain a lot of value from the optimal solution and hurts the optimal solution. So here is the idea. The idea is to do a combined algorithm. So the combined algorithm, until some time ts in the middle, it avoids the element of z. And then, even if they look good, and then later on it continues as usual. And then eventually it returns the best out of the value of z and the value of x, of what you got. Right? So what is the analysis? So don't look at these equations. But if you analyze this algorithm that avoids the value in z, you can see that they give you a lot of value of opt. So alpha ts is 1 over e if you run just this, the simple greedy. But if you put ts equal 1, it gives you 1 minus 1 over e. So it gives you a lot of value of opt. But it also destroys the value. So the value is destroyed by this intersection of z and opt and by the union of z and opt. So these are, I put them in minus because they are positive. So beta and gamma are positive. But then if you see such an equation, you see immediately that you can combine. So you have, here you have positive value of z and opt and z intersection opt. Here you have negative value. So you can take a combination of these two. And then if you choose the right combination, you get this 38.5, which is the best value until now. Okay. So in the few minutes, so 10 last minutes, I will tell you about deterministic algorithms. So you can ask yourself, if you don't like to get a million expectation again, if you can use the multilinear algorithms to just get the algorithms 1 minus 1 over e, or this 38.5. But these were, I cheated in many places in this multilinear. So first, they are randomized in nature because just to get the value of f, you sample from the function. And then already you have this rounding phase that I didn't show you. So in general, they are random in nature. And it's unclear if you can de-randomize them. So maybe yes. It's an open question whether you can de-randomize them. But if you can't de-randomize them, then what you should do is the alternative approach of design simple. Simple is not well defined. Combinatorial algorithm that can be de-randomized. And the first candidate to choose to construct such algorithms are monotone submodular functions, because there we know what is the answer. So we know the answer is, in the randomized case, is 1 minus 1 over e. In the non-monotone case, we don't even know the answer.
So what do you mean by, because previously you're talking about algorithms, and now you're talking about submodular functions as candidates?
No, I'm saying just the first candidate to check if deterministic algorithm hurt you or if you can de-randomize, is where you really understand good randomized algorithms. And this is the case of monotone submodular. So here is a cousin of the random greedy that I showed you before. So this is the residual random greedy. So what will it do? So think about partition method. So partition method, suppose you already chose a dessert and the main course. So you look at the menu and you complement with what you can. So you choose the best side and the best glass of wine and the best first course and so on, right? And then randomly, at random, you choose one of them. Okay? So in general, in method, you complement the independent set into a base, a spanning tree maybe, according to their current marginal, and then you choose one of them randomly. This is the algorithm. And it's randomized, but I will tell you that it can be de-randomized to get our properties. So in partition method, in particular, it has nice structure. So what will it do in partition method? So first, it will choose the best dish, the best main course, the best dessert, and so on. And then choose one of them randomly, and then choose another time randomly. So it's like ordering the partition in a random order and choose greedily by the current marginal. Okay? So the idea here is do not delay dessert to the end. So choose in a random order, choose your meal in a random order. And if you do this, I promise you that you will get at least 51% of the optimal solution. But there are places where it will not give you better than 57%. So this algorithm is good for partition method. But actually, for general method, we don't know if this is better than half. So I suspect that it's better than half, but I don't know. But we can say other properties that are good for our case. So for example, we can say it achieves only half of opt, but it achieves it fast. So if you look at time, if you already chose 50% of or 90% of the portions, then you will get x minus x squared over 2. So I drew it for you. So you will get a lot of value very quickly. Almost half of the value is at when you choose 0.9%. So this is good because if you just here add more value, you get more than half. But as I said, we don't know how to get better than half. And therefore, we need another ingredient. And this one is actually nice. And I think it should be useful somewhere else. So this is a split algorithm. So it will not return you a single base or a single meal. It will split it to two meals that are together independent set or together a base. So think about two children and you want to split toys between them. How will you do it? So think about p equal 1/2. This is for now. So you start and each kid chooses the two kids have the same function of evaluation of the toys. So each one of them choose the best toy with respect to its current set right now. And then if one is better than the other, you give this toy to one of them and otherwise to B. And then again, each one of them chooses the best toy so far. And then if this one is better than this one, then you split the toys between them. And eventually you get two independent sets that are together a base. And you can actually do it with P, which is unequal splitting. And this is something that we need. So what do we know to prove? So we know to prove that this gives you a good combined approximation of values. So for example, if you choose P equal 1/2, then on average, each one of them will get 1/3 of the optimal value together for them. So together, they will get 2/3 of the value for example. But we actually use it for unequal split, and we split it in some different way that is optimized later on. So what you should remember is that you can split the item, get two independent sets that together have a lot of value. So here is the final algorithm that will give you 50.08% of the optimum. So you split the items with some parameter p. You get a1 and b1. And then you randomly use residual random greedy to complete a1 to a base, b1 to a base, and choose the best out of these. And what we can prove is that this improves the greedy that you saw earlier. So just what is the idea of the analysis? So the idea of the analysis is that actually for residual greedy we can prove another theorem that say it will not give you better than half of opt, but if there is another subset T that has a marginal, large marginal value with respect to opt, it will actually give you better than half. So if there exists such a subset, it will give you better than half, but it is unclear if there is such a subset in general. But then what are you doing? You split the items to A1 and B1, and then you can also split opt since this is a metroid. So think about partition metroid to opt B and opt A. So A1 can use opt A to complement its value, and B1 can use opt B to complement its value. And then based on submodularity, we can prove that either opt B has a lot of marginal value with respect to B1, or this term, together they are more than opt. So again, we have two options. Either opt B with respect to B1 is large, then you can gain a lot of value here when you complement this. Or that B1 has a lot of value with respect to opt A, and then you have you have two subsets that can complement A1 to a base, and then residual greedy will gain. So this is more or less the idea. It's not so complex, I would say. So there are lots of questions here, and these should be answered by now, I think. So first, the best approximation, so for monotone functions, we know the answer, but for non-monotone functions and down-closed polytop, there is still a gap here, quite large. These are in percentage. So my guess is that both upper and lower bounds are not tight. So you should be able to improve both of them. And again, this is quite simple. So modular function, think about partition metroid. Just get the right bound. Even for cardinality constraints, in the non-monotone case, there is still a gap here. So it is unclear with non-monotone functions what value can you get. So closing the gap. And then I would say randomization is a question, but maybe even the question of can we use combinatorial approach or simple approach instead of the multilinear, or de-randomize the multilinear extension. So for monotone submodular functions, we can get 1 minus 1 over e randomized. Can we get it in deterministic? So my feeling is that since we were able to break the half, that it should be possible to get 1 minus 1 over e without randomization, but I have no clue how to do it. And in general, do you need randomized algorithm in the case of submodular maximization? Again, this is a question because there is this oracle, black box oracle, and you don't know if you really need randomization in the algorithm. It's not easy to de-randomize the algorithms. Thank you. well, everyone understood everything and can go and optimize some modular functions.
So the simple example that with the earlier question. So if you have two k items, k of which are chocolate cake, and k of which are a value 1 and additive, your k best items on their own in the
Are
first
just a
round
chocolate cake.
are just chocolate cake.
But
And
you
then
should complement this with a submodular.
Oh, this is not submodular?
Right, you need to complement this with all the values for all subsets. Right, so chocolate cake 1 with chocolate cake 2, how much does it worth?
It's anything together
So
with
it
chocolate,
will not
any other
be-
chocolate cake stays at 2.
So it should not be a submodular function, otherwise the proof here is wrong. But this should be the bug. So submodular is very tricky. So constructing things that are submodular is not always easy. So actually, the example of the chocolate cake is just the cut function. And then you can know for sure that this is a submodular function. If it's not a cut function, you start checking it carefully.
Okay,
Thank you.